Okay, so welcome today to the second edition of the distinguished lecture series in business analytics and data science. I guess most of you in the room know me, but for those joining online, my name is Asvin Goel. I'm a professor here at KLU since 10 years, and I will be the academic director of the new study program on business analytics and data science, which will start this fall. Today I'm going to talk about optimization for the masses, no code and no math modeling of decision problems. This is a talk on a current research project of mine. Okay, so I'm going to present about a research project of mine, which is actually a larger project, not like 2 months ago when Henrik presented on AI, he presented about things that are already working. I'm talking about things that will be working in the near future, hopefully. And some of them are already working. And the main motivation of my work is essentially decision problems. And when I'm talking about decision problems, I'm talking about problems where we can formulate the problem as some kind of mathematical model where we want to minimize or maximize an objective function, f of x, subject to the constraints that those x values must be from a set of feasible solutions. So typically what we're talking about in decision problems, when we're talking about mathematical optimization, we have multiple decisions that we can take. Some of them are feasible, satisfying all the requirements that we have in business, and some are not feasible because maybe if we don't have a driver, we cannot send a truck, right? So typically all of those decision variables interact with each other. We cannot freely choose among each other. And of course that is a different animal than like what AI, at least what we are currently talking about, or everyone's talking about, like large language models are doing. Like in one way we could say, well, it is a decision problem to find the most likely word to be answered after another, like one after the other. That's how large language models work. You get a sequence of words, then they calculate the next word that makes sense in the sequence, so they put one thing after the other. And most people think like, okay, that's AI, that's intelligent, and optimization many people don't know, right? But now let's see with decision problems and large language models, they don't fit the bill because large language models are not capable of doing the reasoning behind everything, even though those are all called reasoning models. They are not doing reasoning in a mathematical way, they're doing it maybe in a statistical way or what I assume more in a marketing way, like the reasoning behind that. Like, so when I put in a Sudoku, for example, to ChatGPT or your favorite large language model of choice, chances are that they really quickly prompt you with a solution. And that looks great because it's like, it satisfies all the requirements of a Sudoku and it looks great. But then chances are that the solution doesn't solve your question. Like in this particular example, I flipped the 7 and the 9 from the input that I found in the internet. So I just flipped two numbers and asked ChatGPT again, and it just provided me the answer of the original Sudoku, right? Because it has seen it thousands of times, it has analyzed it, it has calculated properties, and it gave me a solution to the Sudoku that I found online before I swapped two numbers, right? It gives me a perfect solution, but not to my problem. And well, that is not necessarily what we really want when we are running business. We don't want perfect solutions to other people's problems. We want perfect solutions, or at least good solutions to our problems, right? And that's a fundamental difference when we're talking about optimization or larger language model based AI, right? And there's a reason for this. Like when we think about where does it all come from, AI research, essentially, even the term says, like artificial intelligence, we want to mimic humans. So we want to create systems, as AI researchers, we want to create systems that can do things as good as humans. That's the benchmark. Maybe sometimes we're better, right? In terms of writing nice letters and stuff. Of course, the language models are much better than me. Like, I cannot write as beautiful as they. But I do have other qualities, at least some of them. Now, when we're talking about optimization research, the goal has never been to just be as good as a human because, well, then let's just have the human do it, right? We want it to be as good as possible, and usually we can be much better than humans for certain tasks. Maybe not for many tasks, but for those tasks where we can find a good representation and an algorithm that solves it, you're typically much, much better than humans. And so there's a big difference in the baseline where we come from. In AI research, like, we want to be as good as humans, so we need to understand how humans are somehow behaving, and that's what we're doing with data. So we need a lot of data, we analyze that, and instead of having an explicit model of human behavior, we just take a look at what is the result of human behavior. And that's the data, and then we analyze that and have an approach. And then great things are the outcome of it. Self-driving cars, of course. It's great to have a machine driving a car. It will be, on average, much better than the average driver that I see outside, right? I'd be very happy to only have self-driving cars, even if they occasionally make a mistake, because most drivers do regularly make serious mistakes, including me, but sometimes it doesn't matter, right? In terms of optimization, like, well, if we want to be better than human, better than what we've seen, better than what we know so far, like, how do we know whether we're good or not? We need a model that gives us a description of the boundaries of how well we can get. And that's a mathematical model. And so that is the base difference of AI and optimization research, even though some people like put all into AI, right? Like, some people say optimization is AI and vice versa. And of course, a lot of those elements that are used in one or the other area are inspired by the respective other area. Of course, there's some learning mechanism in optimization algorithms, and of course, there's some optimization in training large language models or other AI tools, right? But here's a difference in where we come from, and the drawback is we always need the mathematical model. And with data is available, especially nowadays, much more than it used to be. AI is nothing new. It just became very popular because we have so much data available. So, compared to how many mathematical models we have available for real-life problems, that's enormous what kind of data we have. Now, when we think of optimization, just like, probably it has been flipped in my mind, I'm not on the slide. When we think of optimization, like, the improvement over the last years has just been as enormous as in AI research, right? Like, if we think of just the time it takes to solve a mathematical problem by some common so-called mixed integer programming solvers, Ruby and Cplex, which are the most prominent ones, in the last 20 to 30 years, their performance has improved by 6 million times. Just the algorithm itself, not counting the speed up of the computer themselves. So problems that have been intractable in the past can be solved to optimality today. But on the downside, right, even if we have this map, this is a logarithmic scale. So it looks linear, but it's 6 million times more. So, and it will continue to get faster because brilliant minds are working on this. And that's only for optimal solutions. And our problems are even getting more complex even at a faster rate and bigger global supply chains and so on. So even some problems are not solvable today. But then we have heuristic solvers that just trade off some kind of optimality, some quality against computation time. And then if we think of heuristic solvers and just Hexally to name one, they're capable of creating very good solutions in very little time. So everything that can be modeled somehow can be optimized. And it's just a matter of trade-off between time and solution quality. But again, we need the mathematical model. So what would be the mathematical model for a Sudoku? Right? We have a grid of 9 times 9 numbers. So 81 numbers in total that we have to find, each number having a position. Then certain values are pre-given, but like so we know certain values already. Then in every line we have to make sure, or in every row of the grid, we have to ensure that every number is different. In every column, we have to ensure that every number is different. And then in each of the 9 squares, being 3 times 3, like as they are arranged in the Sudoku, we also have to ensure that all numbers are different. So when we want to solve this, there's nothing to optimize here. We just want to satisfy constraints. So the objective function can be seen as a constant. We can just write it like this, and there's no need as a small print somehow. Like if I was there, I wouldn't be able to read it, but it doesn't matter so much. The thing is, with modern modeling languages, you can just write it like what I said. You have given numbers, you have variables. You have to ensure that all row entries are different, all column entries are different, and in every region, all values are different. But now, on the other hand, even though it's simple when you know how to do it, like riding a bicycle, if you have never seen a bicycle before, right, learning how to ride a bicycle is quite difficult. So probably no one in the room would just be able to just pop out with that model, even though it's relatively simple, right? Now, but then Sudoku is only a small challenge compared to complexities of modern businesses operating worldwide. So now what happens with business problems? Like, it's easy to spoil the fun of Sudoku by just having a solver solving all Sudokus for you, but also that's not the purpose of a Sudoku. It should be fun somehow. Like for me, like the first time I modeled this, it was fun because it was my challenge against my mother, like who was trying to solve the Sudoku, and I said, like, I can implement a solution faster than you solve the problem, right? And so I gave myself half an hour thinking about this, and I was right. But she still does Sudoku, and I think it's good for her, like to stay active in thinking and so on. She doesn't use my solver, which is a good thing. But now when we're talking about business problems, right? Like let's think of a very simple problem again. Like you can't have a much easier business as this Pac-Man business where you run around the street and collect all dots, right? Right? That's the Pac-Man. Everyone knows Pac-Man, or there's also Mrs. Pac-Man, which is kind of a weird name, like, and I think in Futurama there was the gender-neutral Pac-Person once. Now, everyone knows it. So the goal is to run around the streets, eat all dots. Now, if we want to optimize this, what do we need? A mathematical model, right? Now, you know the model. Maybe you don't remember, but I know that you know. But probably not everyone knows this model, right? So what kind of problem is this? Essentially, that is a classical optimization problem that is called the traveling salesperson problem. And typically this is formulated somehow like this by means of mathematical notation. Like who in the room can make sense out of those equations or constraints, right? Somehow, right? Like no surprise, in the room there are more than in average society because That's why we're here learning these things somehow, right? So for anyone who might be curious enough to try to get a glimpse of understanding, essentially what you do is you say, if you have two dots on the screen, like on the street somewhere, you have a distance between those two places. If you want to go from one place to the other, then this distance is like a given value in a Sudoku, right? It's a given value. Then for two places, you also can make the decision whether you want to go from this place to that place, right? So in the objective function, we want to minimize the total distance that we travel by multiplying those distance parameters with our decision variables, which can be 1 or 0. If it's a 1, we travel from I to j. If it's 0, we don't. And therefore, by multiplying the 1 or 0 with the parameter, we collect all the costs. And then subject to the constraint that we want to go to every point that has a dot and eat the dot. And then we also want to make sure that our solution actually forms a sequence of movements starting from the place where the Pac-Man is in the beginning, going from one place to the other, to the other, to the next. And we determine some index numbers like being, this is the first place, this is the second place, this is the third place. Using Big M notation, the favorite in my class on mixed integer programming, right? Now, like reading this problem, we already had some hands going down. Like writing this problem, most hands go down because even when you're actively using this regularly, you still need to think about it to get this right. Even me, like if I see a problem, I still need to think, did I consider everything? Right? Now, this is clearly nothing you can go to, like, can give like a business person running a trucking company or like or a Pac-Man running company, because they would just say like, it doesn't add any value, right? And it doesn't really, like you never solve it using this formulation. Like because it's not what we do in optimization because we can do it better. Now the one thing is even if we follow this path, go for the mathematical model, we develop a solution, then we create the software, we implement it, and then the business is running, shit happens, right? Like the requirements change. Like something is there that we have not considered. And that's the regular case. Like when you go into a company, you want to improve something, you talk to people, you think you have every requirement captured. As soon as you deploy your solution, but did you know that we have those ghosts chasing us? No, of course not, because you didn't tell us, and then you realize the model is wrong, your solution doesn't work. And from a business perspective, this means you have to do it all over. Like the model is shit, the algorithm is shit, the software is shit, that's built upon your business is shit. That doesn't work, right? And that's the reason why many companies, and especially small and medium-sized companies, just don't touch optimization because they are afraid of all these things like what happens if my business requirements change. Business requirements can change either because you become aware that you have a requirement that you didn't know, or because businesses change, right? Then a crazy president of some country, I won't tell the name of, will impose some tariffs, or threaten with some tariffs, or threaten with other crazy stuff. And your business needs to operate differently. And that happens regularly, and if you run a business, you need to be able to adapt because business requirements change over time and there's hardly anyone capable of doing the mathematical modeling, the coding of the algorithm and building the full decision chain on tools that you need. So most people are aware that they cannot afford to heavily invest into software regularly and keep it on time, changing it, and so on. So what can they do? right? No one understands, like if you think of the average person, not you people, like no one can read a mathematical model. Well, those who can don't want to, at least a large share. I don't want to read mathematical models myself. Like if I see too much math notation, I have to decide, do I want to read it? Will it be worth reading it? Because it will take a lot of time and energy for me, even thinking about it. So in many cases, I would just say, nah, I don't want to. Only when I see a benefit. So mathematical modeling is out of the game in most cases. Then programming, right? Yeah, probably a lot more people understand how to program, and they could write and adapt a code and so on. But still, that's only a small fraction of time. And every one of us has seen software that doesn't really do what it's supposed to do. Like we regularly see it, because without a model, without the right specification, the software doesn't work properly. Now, but then there's one thing that really everyone understands. And those are flowcharts, right? Now, if we cannot tell people, give me a mathematical model, or if they cannot prove that the mathematical model is doing what it's supposed to do, if we cannot expect people to describe things in terms of computer programs. Now, flowcharts, actually everyone can read. Even if you have never seen a flowchart in your life, you will somehow identify a starting point, maybe because there is the label start written on it, and then you will be able to follow those arrows and read a bit and go either to one side or the other. And if you end up at the bottom on the right left-hand side, then this is actually what I also would tell you, right? So everyone can read this. There's hardly any training. So now the question is, if we have a language that everyone can read, much better even than natural language, because like you have a comma at the wrong place, the sentence, the semantic is changed. And sometimes even people with the same mother tongue come from different areas where there's different dialects, where different words have different semantic meaning, where even the grammar might slightly differ from one region to the other. Like in India, the English is different than in England, and in England it's different than in Scotland, and in Scotland it's different than in the US or in Jamaica. And everyone is a mother tongue English speaker. And then there are some crazy Germans having their own version of English, right? Even natural language is not precise. Now a flowchart language can be very precise. And if we cannot use mathematical models and programs, computer code, then the question is, can we use something like a flowchart to represent decision problems, the logic of decision problems? And that is actually what we have at hand. The business process model and notation, commonly known as BPMN, in version 2.0, that's the standard since 2012, I think. We have an expressive language that is standardized and that is very easy to learn. It looks like a flowchart. You just draw circles, arrows, and rectangles, maybe with rounded corners, and diamond shapes, and so on. And you can describe how a business process is working. And a one-day workshop will be enough to understand at least 80 or 90% of the language. And then if you want to dive in deeper, another day maybe is necessary, or if you want to really become an expert, maybe a bit more time. But essentially, with very little training, you can understand this business process model and notation language, which is very expressive. And the research that I'm conducting here is actually using this language to specify optimization problems so that no one needs to write the mathematical formulation of a traveling salesperson problem, for example. And this is like at least the working title, BPMN OS, BPMN for optimization and simulation of business processes, which allows to provide all information that is necessary to formulate certain types of optimization problems, which is 100% compliant with the standard. So all the tool sets that you have around will be working with it. And the idea is essentially that you take the visual representation of a business process model formulation, you enrich it with some data that is relevant for execution, like an execution model where you have certain requirements modeled, certain data attributes modeled, certain ways how data attributes are modified when the process advances. And then you take the so-called instance data, like your actual thing that you're working on as a business problem, like your today's customers, the list and addresses of those customers. You put it all together and you combine the visual representation with your data and the execution logic, and you obtain what is called a state machine. And with that state machine, essentially everything is captured that you need to solve. Certain things can be done automatically, and at some points, an actual decision has to be made. And then whenever a decision is made, either a human or a computer algorithm will give a suggestion for how to decide. And decisions in this case would be, when do I start with an activity? Sometimes it makes sense to start directly, sometimes maybe only later. Because why should I go early to a customer if the opening times of the customer don't make sense to it? Like, I don't want to go like to Edeka at 5 in the morning, right? So I'd rather delay the start. Also, another decision is when an activity ends. Then when I send a message, I need to make an assignment of recipient and sender, like who gets my message? Like in postal services, we write an address. Similarly, sometimes we have we shout out to someone and then we see who responds, right? Sometimes it's clear where a message goes to, sometimes we need to figure out while doing things. And then sometimes we actually have to make some choices, like picking an order value, like a quantity value that we decide on. Now, those are 4 types of decisions, and everything else can be automated without any input, just by having the state machine executing one step after another of a business process. And now here's an example of the traveling salesperson problem that we've seen, like with the Pac-Man running around eating the dots. We've seen the mathematical formulation where probably all of you would not remember exactly what the formulation would look like. Some of us have seen it often enough so that we somehow have a feeling. This is the traveling salesperson problem in BPMN, where we just have a very simple process that starts at a point, which ends at a point. Then in between, we need to visit some locations. Those are the locations of the dots. The BPMN logic says that whenever we have those 3 parallel bars on an activity, which is this rectangle shape with the rounded corners, whenever we have the 3 bars, it means we have multiple locations to visit, right? So we start somewhere, then we have multiple locations to visit, like all the dots of the Pac-Man graph. And then after we visited all of them, we return back to wherever we want to go back, like back to the depot or back home, right? And then there's just some little data that you have to provide. For example, like the parameters that indicate how much it costs going from one place to another, like a distance table. And of course, we need to store the location where the Pac-Man is to know where it can go, right? And now, with such a formulation, I think it's quite evident that with very little training, it will be possible to explain someone based on a graphical visualization of the traveling salesperson problem, what it's meant. to be compared to the mathematical model, where you really need some heavy training in math notation and constraint building and so on, right? And there's very little to teach, and it's fully automatable, right? You can use this to actually optimize or find an optimal route of the traveling salesperson problem. Now, in the research that I'm doing and the framework that I'm building, so far I'm not there where I want to be yet, right? Because things always get a bit more complicated than when you start. But what I can do already is like to optimize based on local decisions, essentially doing some kind of greedy algorithm, or what is called a greedy algorithm, meaning like that you, wherever you say you are, you go to the next place, the closest place, for example, which makes a lot of sense, right? Why not eat the dot close by instead of running around all over to the other side first, right? But the current research, and that's what I'm doing in my every free time, I'm coding and trying to build optimization algorithms that can even do much better. Right? That's a nasty thing. I had hoped that I'd be done already, but it will still take some time. But it will not take years for a better algorithm. And then, of course, someone else will be even capable of doing something even better. Now let's just go through some alternative models, and you'll see how much this framework is capable of doing compared to mathematical notation, right? Some of you might have heard of the so-called assignment problem. The assignment problem is always when you have like two groups of elements and you want to assign every element of one group to exactly one element of the other group. For example, if you have clients who need some server, you want to have an assignment of a client to a server. Like some people can serve the task better than others, like they could be humans, it could be machines or whatever. And so you have some kind of assignment cost. This client essentially says, I need a server, sends a message out, and this message will be delivered to one of the other servers based on minimal costs, essentially. So typically you have multiple clients, multiple servers, and you need to match each one of them at the least cost. You think of a mathematical model, that's the simplest optimization problem that I know of, but still it will be kind of complicated for people who don't use this regularly. With this visual representation, it's much easier, and it's easy to adapt. If you realize your processes change, you not only need one server, maybe you need two, everyone can change this model. Let's think of a vehicle routing problem, which is essentially an extension of a traveling salesperson problem, where you don't only have one salesperson, but you have a fleet of vehicles, and every vehicle has a capacity, so it cannot visit all the customers or dots, right? Then if you think of the mathematical formulation, that's already a very small font size, so you probably won't be able to read it. That can be done. There's tons of others mathematical formulation, but all of them hide a very important information. If you are only given the mathematical model, you don't have an idea of what's actually going on. Now, if you think of the visual representation, we have a customer process, we have a vehicle process. The customer process is very simple. Essentially, you ask for a vehicle, you wait for the vehicle to arrive. If the vehicle arrives early, you wait until your doors open. You handle the shipment, and you just tell the vehicle the shipment is handled. Very simple process, which actually fits very close to what businesses are actually doing. And if they change what they're doing, maybe they say, well, first I need to inspect something, or I need to have an extra step of work here and there. People can change it. On the vehicle side, essentially, it's for every now and then they will receive a request, then they are to fulfill the request. So they have to drive to the location of the customer. Then they have to tell the customer that they have arrived. They wait until the shipment is handled and then it's done. And then they can do the next thing. And at the end of the day, essentially they will return to the depot. Right? So even here, having a model that is kind of close to how business actually operates has its own value compared to a mathematical model, which is only good for computers, essentially. And for mathematicians who like to work on those problems. Because sometimes abstraction is good, but in many cases, you really want to understand what you're doing. You want a formulation that is close to what you're doing. So what does the framework that I'm building do? It actually unifies modeling. We have one model that can be used for documentation of business processes, which many people actually use anyhow, right? They use BPMN, that's how it was invented, mainly for documentation purposes. But then also the same model that we use for documentation purposes can be used for simulation and automation and also for optimization, right? And the traditional way of doing things is like someone describes a business process. In many companies, we are like, we need to understand our business process. How do we do things, right? And then it's a whole lot of work diving into the processes. And then you have your documentation of the processes. You put them in the folder and you lock them in a locker and you never touch them again, right? That's how many companies work, like including one or the other company that I have worked for. Like when processes are only documented for the purpose of documentation, they are not being used. Now, if you, however, have the processes documented and you can use the same model for doing things better, then people start using those processes, and that's where the benefit comes from. And you can have like a full automated cockpit running your business, essentially. And BPMN OS does not only unify modeling, it also democratizes optimization, because many more people will be able to formulate an optimization problem compared to the status quo that we have today. In a way, it is like Excel spreadsheets for simple calculations. Like in the old days, accountants had to do all the calculations and fill in their sheets. And then Excel spreadsheets came, and then you had a formula here and a formula there, and everything was much more efficient. The same thing can happen with business process models for optimization. So, and with that, I come to the end of this presentation. Essentially what we have a modeling framework that is already done, it already works for simulation. It is easy to learn. It's unified because it can be used for documentation and automation and simulation and optimization. And it's agile because it allows the problem owner who knows about the business problem to change it. Every now and here we know. Sometimes we do things in a different way, and then the problem owner should be capable of adjusting the system. And compared to mathematical modeling or hiring an IT company to build a solution, well, that works for one goal, but when requirements changes, it's another very important, heavy task. All of that is available online as code, open source. It will be developed over the next months and years and maybe even longer. There's a lot of things that can be done in this area, including master thesis, bachelor thesis, or even PhD thesis, because that is just a very young piece of work, even though I spent most of my time of the last years on this. A lot of things can be done in this area. A lot of exciting things can be done. And I'm pretty assured that, like, in terms of optimization, we will see it much more, because sooner or later we will realize that large language models, or AI, how we see it, will not deliver everything that we wish it could deliver. AI will dominate us for the nearer future and the further future even more, but only for select tasks. And then when we want to see how good can we be, we need to go the step further and do optimization. And with that, I close this presentation, and I guess we do have time for questions, if you have any. Yes, please.
Yeah, just from a non-research perspective, this business process modeling that you are using, is that like one of many solutions that's trying to solve the same problem? Is it this solution that will play a big impact, or is it like something that you do because you're really interested in it? And just to give us a perspective of the impact this will have.
Okay, so the question is, if I can rephrase it in my own words, whether BPMN, like the language for modeling business processes, is just one out of many options. And here the answer is clearly no. BPMN is the de facto standard of modeling business processes that is already applied very widely, right? Of course, there are other ways of modeling, like using those non-standardized flowcharts, but BPMN is the go-to solution if you want to have a more formal approach.
I meant more in this method that you're describing to formulate.
Now, to the method to formulate optimization problems based on business process models is, of course, something new, which is my current research. But so far, like what I observed, but I might have been missing certain elements. The world is evolving quickly. So now, when we think of research being conducted in optimization, the main goal is I want to get better in solving this optimization problem. So people go for efficiency of the algorithm. But the ease of modeling is often not understood as a problem. So like smart people, like mathematicians, computer scientists are all working on those problems, and they've learned it since they were small at university, and they learned it, and they see it as a given. So now, on the other hand, outside of this community, no one knows how to model like this. And in that community, no one knows BPMN. And if we have a language that is widespread, that has a powerful expressiveness, and if we have methodologies that are highly efficient, then for me, the natural choice is we should put them together. But that, of course, is like the idea that drives my research, whether it will be successful in the end, or whether someone else comes up with another idea, just saying, well, we skip the modeling part altogether and we have a large language model describing the problem, which I would see very skeptical, but maybe there's a tweak that will make it possible. Of course, that is debatable, like everything in research. Yes, please.
We have a question in the chat from Paulina, and first of all says, thank you, great presentation.
Thank you.
And her question is, what is the difference with process mining?
The difference with process mining, a very good question. Process mining is a very hot topic as far as I know, a topic that I don't know very much about it, to be honest. But the goal of process mining is essentially taking the data that you have in companies, event logs, like certain things happen in the company, you have your systems that record those events, and then you have a protocol of what has happened. And the idea of process mining essentially, as to my understanding, is that you want to understand how your processes actually work based on the data that you have, because like many companies, they just evolve and different players, stakeholders are involved. So you don't know exactly how you're doing this. Like if you ask me about certain things, how they work at this university, the most likely answer would be for me to say, well, I need to ask someone else because I don't know, right? And in the larger a company becomes, the less likely it is that you actually know what you're doing. Like, because people are doing things anyhow, because like those people on the job know what they're doing, but then they don't know what other people are doing. And process mining is there to get a common view on overall process efficiency, to see where things have, what has happened, in which sequence, whether there are requirements that are important or whether there are things that could be changed to leverage some potential. Now, that work that I'm presenting will build upon process mining. Once you have an understanding of your processes, then you know, based on data, then you know what you're doing, but you don't know what you should be doing. And with optimization on those process models, you can actually improve what you're doing. So that's the next step after process mining. So I think both go well hand in hand. Thank you. Christian.
You said that you are not the place where you wanted to be. You are experiencing some challenges.
Oh, in terms of the implementation.
Implementation, yes. Especially you're working on locally, you're having some success, some degree are going on, but where are the main challenges?
What are my main challenges? Essentially, when I started this, I made a lot of simplification and decided for myself, this will be doable. I will not need years for it. But then while doing it, I realized that there's no need to only focus on a certain subset of features. I can cover the full specification of BPMN. And however, when you want to be more generic, certain design choices need to be different. Mm-hmm. And then it becomes a bit more complicated. So essentially, while doing what I'm doing, I realized I can even solve a larger variety of problems. And that is essentially the main challenge. Why I'm not there where I want to be in terms of implementation being conducted, but where I know I will get there and it will be even more powerful. So I'm putting a bit more upfront investment to have a more widespread applicability. That's essentially the trade-off that I take. Any further questions? Yes, please, Günther.
Yeah, the BPMF software you have mentioned. This is a software used to visualize the optimization problem, or does it solve the optimization
So
problem?
BPMN itself is just a language description how to write models and how to exchange models from one system to another, like with a documented XML format behind it. The framework that I'm developing is actually like putting an extra layer on top of that, because the BPMN standard itself says it just wants to show how processes are defined, but not how they are executed. So BPMN itself as the language doesn't say like if the logic tells you you're about to start that task, it doesn't tell you that you need to start it now. It just says you're all set up to start it. Whether you do it now or next day, there's nothing in the specification of BPMN. And BPMN OS is designed in such a way that it makes those missing decisions that are not specified, which might also be case dependent. For one customer, you might want to decide like this. For another customer, you might want to decide differently. Or if you have a collection of customers, you want to prioritize some, even without knowing. So that is the extra layer that I'm building.
And the and why start this with BP, with business processes? So what I understand is that you can use it for optimization problems of any kind. So let's say civil engineering, you want to build a bridge and you want to say minimize the costs of building the bridge, and the constraint is it must be stable.
Yeah, but physical constraints often look differently. Like like building a bridge is to some extent a mix of physical requirements and processes. Like to build a bridge, first you need to find the right spot, then you need to build the pillars and so on. So that is a process view. For that part, surely you can use it. The physical constraints, on the other hand, like they might be based on whatever, like differential equations. That would not fit into the BPMN OS framework, but once you have the parameters, you would be able to put those requirements on, like, we need that material quality, we need that durability, that flexibility parameter that you could put in there. So yes and no, like it will not be able to solve any kind of optimization problem, but many optimization problems that we regularly have can be viewed as a sequential decision problem where we have to make one decision after the other. And that's exactly what business process modeling and notation has focused on, showing which sequences of activities are to be conducted.
Yeah, I'm wondering about the level of detail that the processes are defined in the BPMN, because the more detail I get, the more limited the solution will be, right?
Like the nice thing about BPMN is that it allows you to use what is called a sub-process, which is looking like a box, like a regular task, but you can dive into it and get more details. So you can provide different layers of abstraction to different people, so that it does not become like a full wall of diagram. If you build an aircraft, right, you would have like, you start here, then you do this and that and this and that, and then even the wall would be too small. You can provide different levels of abstraction within the same model. That's a good thing. But of course, like if you think of what kind of detail you need, you will never capture the full world.
Yeah,
You always need to define your scope.
Yeah, or the other way around, you have a business defined as minimize money in, maximize money out, and you cannot do anything with that. But
Right, the BPMN model logic allows you for certain parts of a business model, let's say. Like if you're like, it's not a business machine in the end. Like it will, certain tasks that are being done in a business will be, you can create a very detailed model on doing this very precisely. But of course, if you do everything very precisely, it will be a lot of work, and maybe reality changes meanwhile. Yes, Anne.
So thanks, Asvin. So it was a great talk. So I was wondering, you showed us that you very efficiently can translate a BPMN model to a mathematical model. At the beginning of your talk, you showed us how to use large language models to use text input and create a mathematical model out of it. Couldn't you also use large language models to use the BPMN model, create text out of it, and then use the model again to create the mathematical model?
Essentially, yes. Like there has been research, like going in any direction. Like for example, taking a textual description of a business process, creating a BPMN model out of it.
Yeah.
That would be one path. Like to go into existing documentation, create a BPMN model out of it, then enrich it with some execution relevant information and use a framework like this, or even the other way around, taking a large language model and directly creating a mathematical model out of it. Then the large language model will not be able to solve it, but other tools could solve it. If the large language model actually modeled your problem and not some other problem, where I still see a big hurdle that, like, what AI is really exploiting heavily is the benchmark is the human, and humans are, like, at least I, to some extent, I'm really stupid, right? I don't want to say anything about you guys, probably you're smart, but a human as a benchmark makes mistake. So mistakes are acceptable in all of the AI research that I've seen so far. And if you accept mistakes, and in many cases you can accept mistakes, like okay, it hasn't been a cat, it was a dog, right? Not a big deal unless the cat was a lion and you get eaten, right? But for a lot of tasks, it's absolutely okay to make mistakes every now and then if you improve over alternatives. Now, however, if you cannot afford to make mistakes because then you have a serious disaster or you go bankrupt or you have like, oh, my large language model said like my tsunami wall only needs to be 9 meters and the flood wave is 15, right? Then that's shit. And then you don't want to have a stochastic machine in between that by design makes mistakes, like we as humans. As humans, we make mistakes, that's a fact, and large language models make mistakes. You will see it on all large language models. ChatGPT makes mistakes, DeepSeek makes mistakes. They even say it, like, please check what you're using. Many people ignore it because the quality is surprisingly good. Good for most purposes, but if we want to make sure like that we don't have a blow up of a nuclear power plant, we rather use a real model rather than a stochastic model. Okay, if there are no further questions, then thank you for showing up or attending online. Before we go, there will be another edition of this lecture series in exactly 2 months' time. On the 2nd of April, first Wednesday in April at 6 p.m., Arne will present on optimization topic on solving sequential decision problems. Actually, something very related to this presentation because that's essentially what I need to solve in my business process models. One decision has to be taken after the other in a certain sequence. He will tell us the details on how we can do this. So very well worth attending this lecture on the 2nd of April. And if you are interested in even learning more, we will have a new study program on business analytics and data science starting this fall for all of you who are interested in that. Okay, then with that, thank you and have a nice evening. Bye-bye.